Hello, this is lesson 5.2 on matrix representations of a linear transformation. This is the last section of this course. We are continuing with coordinate transformations. Now we're going to take two vector spaces, u and v, with a linear transformation between them, and take the two coordinate representations for u and v so that the transformation between the coordinates becomes a matrix transformation. So this is called a matrix representation of a linear transformation. So I'll start by just conceptually drawing what we're going to be doing. So we're going to take two vector spaces, u and v. The dimensions of these vector spaces can be different. So the dimension of u we'll say is n, and the dimension of v is m. And we have a linear transformation from u to v, and we'll call it t, which takes a vector u and maps it to its image t of u in v. So what we're going to do is now define two coordinate transformations using a basis for u. So we have a coordinate transformation TB, where B is the basis for u. And this will associate the vector u to its coordinate representation, or its coordinate vector, u sub b, which is a vector in Rn. Because u has dimension n and TB is an isomorphism. We're going to do the same thing on the other side here. We're going to take a basis for v. This basis will have m vectors, and we'll call that basis b prime, and define a coordinate transformation t sub b prime, which will map the vector t of u to its coordinate vector t of u sub b prime, and this will be a vector in Rm. And finally, now we have a vector in Rn and a vector in Rm. We're going to define the transformation that goes directly from the vector ub to the vector t of u sub b prime. And this is a matrix transformation. And because TB and TB prime are isomorphisms, these spaces Rn and Rm preserve faithfully everything that concerns the vector spaces u and v. And that includes the transformation T between u and v is faithfully represented by this matrix transformation between Rn and Rm. Because it's a matrix transformation, you can write it using a standard matrix. This is matrix transformation of T. And it will have a standard matrix M. The goal is to find this matrix M. So to define everything that we have in this little diagram here, formally, so T is a linear transformation from u to v, which are two vector spaces. So u is a vector space of dimension n. We're going to equip it with a basis b that has n vectors, so we'll call this u1 to un. And we also have the coordinate transformation TB, which goes from U to Rn. So it's a coordinate transformation relative to the basis B. And we're going to repeat the exact same thing for V. So it's a vector space of dimension m. So it has a basis B prime with m vectors, and we can call these V1 to Vm. And we have the transformation T sub B prime, which goes from V to Rm, which is a coordinate transformation relative to B prime. So now that everything is defined, we can define the topic of this section, which is the matrix representation of T. So which again is going to depend on the choice of our two bases, B and B prime. So it's a transformation from Rn to Rm, whose standard matrix is M, which is to be defined. That will be the goal of this section, is to define the matrix M, which represents the transformation T. So the advantage is that it's always much easier to work with matrix transformations for all kinds of reasons. They're more conceptually easy to grasp, and they're computationally a lot easier to implement on a computer. So if you want to work with a transformation between two abstract vector spaces, which can be function spaces or matrix spaces or polynomial spaces, it's often much easier to do this process of using two coordinate transformations to bring it down to the level of Rn and Rm, so that we can work with matrices instead of working with an abstract transformation. So our main goal in this section is to find this matrix representation M for the transformation T from U to V, which means that we want to find the matrix M such that if you take the coordinate vector of a vector U relative to the basis B, which is chosen for the vector space U, left multiplied by the matrix M should give you its image, which is the image of U under T, coordinate under the basis B prime, which is the basis chosen for the vector space V. So, and this here is the standard matrix that we're looking for. So for this, we're going to start with an arbitrary vector in U and go through the process of writing it according to the bases. So starting with an arbitrary vector little u in U. And because U is a vector in U, you can break it down into a linear combination of the bases B, C1 U1 plus C2 U2 all the way to Cn Un. And we can take its image under T, which will be T of C1 U1, etc., all the way to plus Cn Un. And because we assume that T is linear, we can pull out the constants and break out this addition to C1 TU1 plus, etc., to Cn TUN. And that's because T is linear. So now we're going to take each one of these vectors, U1 to UN, which now have their images TU1 to TUN, and break each one of these according to the basis vectors of the basis V. So we're going to take all the basis vectors in V in B as we did here, take their images, and write them as linear combinations. Now with the basis vectors in B prime, which are the V1 to Vm. So that means that we're going to take the first image of the basis of U, which is T of U1, and break it down into a linear combination of the V's. And so we'll have coefficients A11 V1, etc., plus A1M Vm. Same thing with all the other vectors, all the way down to T of Un, which can be broken down into AN1 V1 plus all the way to ANM Vm. And now we can substitute all of these expressions back into this expression up here. So this equation right here becomes T of U equals C1 times this expression right here plus all the way to the last one, which is Cn times TUN, which is AN1 V1 plus all the way to ANM Vm. And we can shuffle around all of these vectors here and rewrite them, combining them or regrouping them by the vectors V1 to Vm. So the first coefficient will be C1 A11 plus C2 A21, etc., all the way to Cn An1, and this all multiplies the vector V1. And you can do the same with all the others. The last one will be the vector whose coefficient is C1 A1m plus C2 A2m, etc., all the way to Cn Anm times the vector Vm. So we now have an expression for t of u written as a linear combinations of the vectors in B prime. So we can write the coordinate vector t of u relative to B prime, which is the vector whose components will be c1 a11 plus cn times an1 as the first component, and then the other coefficients will be the other components going down until c1 a1m plus can anm. So this vector can itself be broken down into a matrix times a vector. The matrix A11 through AN1 across and then down to A1M and over to ANM times the vector C1 to Cn. So if we observe what we have here is a matrix whose columns are the coordinate vectors of the basis vectors, the images of the basis vectors in B relative to the basis vectors in B prime. So you can write this column by column, where each column is going to be tu1 relative to B prime, all the way to tun relative to B prime. And c1 to cn, if we just look above here, is just the coordinate vector of u with respect to B. So we have found the matrix M that we were looking for. It's this matrix right here. So we see what M is. It's a matrix whose columns are the coordinate vectors of the images of the basis B relative to B prime. So we can write this as a theorem. Columns of M are the coordinate vectors of tu1 through tun, so the images of the basis vectors of B. Relative to B prime. So that's how you can build this matrix M, is just column by column. And so what you obtain then is a matrix transformation. And this matrix transformation is the representation of T, and it faithfully preserves all the properties of the transformation T. So we can write that as another theorem here. The matrix representation of T, so, is a matrix transformation. With the same properties as T. Which means that if T is 1 to 1, the matrix transformation will also be 1 to 1. If it's onto, it's also onto. So things like 1 to 1, onto, isomorphism, all these things are faithfully preserved in the matrix representation of a transformation. So let's look at an example. So let's take a transformation from P1 to P2. defined as follows. So we'll take t of a vector in P1, which is a polynomial of degree 1, ax plus b, and we will say that it maps it to the polynomial in P2, 5ax squared plus 2, or a plus 2bx plus a minus 3b. So we're going to choose a basis for P1 and a basis for P2 and find the matrix representation of T. So let's take B equals the canonical basis x1 and we'll take B prime. We'll also just take the canonical basis for P2. So x squared x1 so we want to find the matrix representation of T. So according to what we just derived, this matrix that we're looking for is a matrix whose columns will be the images of the basis vectors u1 and u2 relative to b prime. So we can do this column by column. So first starting with t of u1, which is the first vector in the basis b, which is the vector x, so t of x. If you plug the vector x into the function t, so it's the vector such that a equals 1 and b equals 0, so on the other end this gives you 5x squared plus 1 times x plus 1. So this is t of u1, and now we need to find tu1 relative to b prime, where b prime is the canonical basis x squared x1. So the coordinate transformation will give you that tu1 relative to b prime is the vector 5, 1, 1. This will be the first column of our matrix M. We do the same thing for the other column. You take the second vector of B, which is the number 1. You plug it into this transformation. So 1 is the polynomial such that A equals 0 and B equals 1. So when you plug that in, this gives you 0x squared plus 2x minus 3. And when you write this relative to b prime, it gives you the vector which components 0, 2, minus 3. So now we can take these two columns and put them together to obtain the matrix M, which will be a matrix with columns 5, 1, 1, and 0, 2, minus 3. It makes sense that this is a 2 by 3 matrix because it goes from a space of dimension 2 to a space of dimension 3, in other words, from R2 to R3. So the dimensions are correct. So we can do a test run. So let's take a vector u in P1 completely arbitrarily. Let's pick the one 5x plus 2. So let's take the image of 5x plus 2. When you plug it into this function t, 5x plus 2 is a polynomial where a equals 5 and b equals 2. So this gives you the image 25x squared plus 9x and minus 1. So now we can write the representation, or the coordinate vector with respect to b prime, the vector 25, 9, negative 1. So now we'll see if we can obtain the same vector by first taking the vector 5x plus 2 and writing its coordinate vector with relative to b, which is the vector 5, 2. And now left multiplying this by our matrix M. So you're multiplying this matrix by this vector. And the result of this matrix multiplication is 25, 9, minus 1. So you observe that you obtain the same vector taking both routes, which means that everything is correct. So to get a visual representation of what we just did here, we started from a transformation from P1 to P2, which are these two vector spaces. Each one of these two vector spaces was equipped with a basis, the canonical basis in both cases. The canonical basis b for P1 is x1. The canonical basis b prime for P2 is x squared, x and 1. We use these two bases to define two coordinate transformations, TB and TB prime, which map down to R vector spaces of appropriate dimension, R2 for P1, because P1 has dimension 2, and R3 for P2, because P2 has dimension 3. And then we defined a matrix, which is the matrix, the standard matrix of the matrix transformation that represents T. And then we did a test run with a arbitrary vector 5x plus 2 in P1. And we arrived at this bottom right-hand corner by two different routes, either going across and down, or first down and then across. So first what we did is we plugged 5x plus 2 into the function t, which gave us 25x squared plus 9x minus 1. And then we wrote this polynomial as a vector in R3 using this basis, which gave us the coordinate vector 25, 9, minus 1. Then what we did is we came back to 5x plus 2, and we took the other route by first writing 5x plus 2 in terms of a vector in R2 using the basis x1, which is the vector 5, 2. And then going from 5, 2 to 25, 9, minus 1 simply consists in multiplying this vector by the matrix that we calculated, the matrix 5, 0, 1, 2, 1, minus 3. So the advantage is that now if we want to study this transformation T, we can just study the transformation M, which is a matrix transformation, a lot easier to deal with. And everything is equivalent between T and M. For example, if we want to find the kernel of T, instead of finding the kernel of T directly, we could just find the kernel of M, and it will be equivalent. So let's ask the question instead, what is the kernel of M? So to find the kernel of M, we just want to solve for mx equals 0. So in other words, the solutions of this matrix times x1, x2 equals 0, 0, 0. And this is just a linear system that can be solved by Gaussian elimination or any of the other solutions or methods that you want. If you write this as 5x1 equals 0, x1 plus 2x2 equals 0, and x1 minus 3x2 equals 0, you see easily that x1 and x2 are 0. The trivial solution is the only solution. So the kernel of this matrix is the 0 vector. That means that the kernel of T is also the 0 vector. So the fact that the kernel of M is 0, which means that the transformation M is 1 to 1. And so this means automatically that T is also 1 to 1. So as you see, you can work on the level of M or at the level of T, and everything is faithfully preserved. It oftentimes makes more sense to work on the level of M because we're working with matrices, which are a lot easier to deal with. There are many other advantages. Matrices are a lot easier to deal with computationally if you're working with a computer. In differential equations, there's all kinds of transforms that allows you to solve a differential equation using this method. For example, Laplace transform or Fourier transforms work this way. A Laplace transform takes a differential equation and converts it to a Laplace space here, where the differential equation becomes a simple linear system, which you can solve, and then take the coordinate representation back to the solution space. It's a lot easier to solve a linear system than it is to solve a differential equation. And that's the purpose of using these transforms in that particular application. So finally, in this case, we used a canonical basis in both cases. As you'll see in the exercises, sometimes it makes sense not to use a canonical basis, but to use, for example, a basis of eigenvectors. The advantage of doing that is that the matrix transformation, or the matrix representation in that case of the transformation becomes extremely easy. If it's a square matrix, it becomes a diagonal matrix whose elements are the eigenvalues. So you'll see in the exercises, if you take transformations in which we use basis of eigenvectors instead of just a regular canonical basis, it makes the matrix representation extremely simple.